Okay. So let me bring this up. All right. All right, so let's commence with this discussion, properties of solutions. And there'll be a bit of a review as far as the initial part of this chapter is concerned. So let's begin. So we all know what a solution is, right? A solution is a homogeneous mixture of two or more substances, all right? Okay, so there are two parts to any solution, of course, we know. One part is a solute, and the other part is a solvent. And usually, the part that is in greater amount would be the solvent, and the part that would be less amount would be the solute, right? Now, of course, we all understand and know that matter or substances exist in three major states or phases, right? You have the solid, liquid, and gaseous states, right? So basically, when it comes to solutions, you have different possibilities based on the different phases. So as you can see in the table below, you can, for example, have a mixture of gases, right? And that is a solution. It's a homogeneous mixture by definition, so it's a solution, right? So an example of that would be the air we breathe, right? The air we breathe is mostly nitrogen, just under 80% nitrogen, and then the next more abundant gas would be oxygen, which is less than 20%, and then you have some other minor gases in terms of amounts. You can also have a situation where a gas is dissolved in a liquid, all right? So a good example of that would be carbonated beverages, like Sprite and Mountain Dew and all that, right? They all contain carbon dioxide dissolved in those solutions, in addition to other things like flavors and so on. Now, this one is a bit unusual, but believe it or not, you can have a gas dissolved in a solid, right? And one example of this would be hydrogen gas dissolved in palladium. That's a very special reagent that you will meet if you plan to do organic chemistry, because that is very useful for carrying out certain reactions, certain organic reactions. You can also, of course, have two liquids dissolved in each other. So an example of that would be ethanol and water. And then you can also have a solid dissolved in a liquid like sodium chloride and water. And then you can have two or more solids dissolved in each other. So some examples are given there. Brass, for example, is a mixture of copper and zinc, and solder is a mixture of tin and lead. So these are all examples of solutions, all right? Okay, so let's talk about different types of solutions in terms of the level or the amount of solute present in the solution. And there are three categories. The first of which is what we call a saturated solution, right? This is a solution which contains the maximum amount of solute that the solvent can accommodate, depending, of course, on the amount of solvent, all right? At a specific temperature. So whether or not a solution is saturated is actually temperature dependent. Then you have what is known as an unsaturated solution, which is one that contains less solute than basically what you will see in the case of a saturated solution, again, at a specific temperature, all right? And then the third category is known as a super saturated solution. And in this particular case, this solution contains actually more solute than what is required for a saturated solution. Because of that, it is very unstable, all right? Unstable in the sense that if you achieve making this solution, pretty much anything you do to it will result in some of the solute coming out of solution. And I think I have some pictures here in the case of a solution of saturated sodium acetate, right? So this is your saturated solution of sodium acetate. And what this person did was just add one crystal of the same substance to the solution, and you get the spontaneous formation of sodium acetate crystals coming out of solution, and the resulting solution will become eventually become saturated, all right? So that's basically what we mean by a super saturated solution. And as I said before, pretty much anything you add to it will result in the formation of crystals. So if you take a piece of glass, for example, and add it to the supersaturated solution, the same thing is going to occur, right? Or if you even shake it, the same thing is going to occur, all right? You're going to see the formation of solid coming out of solution. Okay, so those are the three different types of solutions that, in terms of the level of concentration that exist. Okay, now let's look at the type of interactions, the microscopic interactions that will take place when you have a solution formed from a solute added to a solvent, right? So if we look at it in terms of energy changes, well, before we look at energy changes, let's look at what happens in terms of the type of forces that exist between the particles, right? So basically, there are three types of interactions that you have to consider. You have to consider the interaction between solute particles. You also have to consider the interaction between solvent particles. And then thirdly, you have to consider the interaction between solute and solvent particles when they mix, right? So we can look at the type of energy changes if we break down the dissolution process in terms of these types of interactions, right? So I have a diagram here which shows you pictorially what is happening when it comes to the formation of solutions from mixing a solute and solvent. So here are your solvent molecules. The molecules would have certain forces between them. You'd have to break those forces in order to achieve dissolution. So that's what's happening here in step one. And whenever you're breaking those forces, that will require energy, right? Which means that this process will be endothermic. I'm sure you're familiar with that topic, that term, right? What that means, therefore, is that the enthalpy change for that process would be positive. So let me make a note here. I probably should have typed that in, that delta H1 will be positive, right? And then now, over here, we have the solute particles. You also have to use energy to break up the forces here between these particles. So delta H2, which is the enthalpy change for that process, separating those solute particles, that also will be positive as well. And then we get to the combination of the solute and solvent particles to form your solution, right? Now, of course, what's going to happen is that you're going to have forces between the solute and solvent particles, right? So therefore, bonds are being formed, and as a result, the enthalpy change for that process would be negative, right? So basically, we have a combination of endothermic and exothermic processes occurring as you're going from your separate solute and solvent to your solution, all right? So basically, for the overall change in terms of the energy, the enthalpy change of the solution will be equal to the sum of the enthalpy changes of the different processes that we described earlier. Delta H1 plus delta H2 plus delta H3 is going to be equal to delta H of the solution. And whether or not delta H of the solution is exothermic or endothermic, of course, is dependent on the relative magnitudes of these delta H values. All right, so for example, let's say that this part here is large and positive, and this part here is small and negative. That means that delta H solution would be positive, all right? And as a result, the solution process or the dissolution process will be endothermic, all right? Okay, so that's what happens when you're making a solution. Now, there's a general rule of thumb, that's why they have a thumb here, called like dissolves like, when it comes to predicting whether or not a solution will be formed between two substances, all right? And basically what they're saying is that if the intermolecular forces between the separate components of the mixture that you're about to make, if the intermolecular forces are similar in those separate components, then they will mix, right? Because the intermolecular forces will be similar in the solution as well, right? So basically what they're saying here is that, basically the conclusion that we can come to based on this rule of thumb is that nonpolar molecules will be soluble in nonpolar solvents, all right? And I think I have an example or two here. So for example, carbon tetrachloride will be soluble in benzene because both carbon tetrachloride and benzene are nonpolar, all right? Then we have the possibility of polar molecules. When you add them to polar solvents, they will be soluble as well. And an example here would be ethanol when you add it to water. And then I have a third example here, which deals specifically with ionic compounds. Now, when it comes to polarity, you cannot get more extreme than ionic, right? Ionic is basically the extreme of polarity. And what you'll find is that generally speaking, ionic compounds are more soluble in polar solvents, all right? So that's basically the rule of thumb as far as predicting whether or not a particular solute will dissolve in a particular solvent. All right. So here's the example of an ionic compound soluble in something polar, sodium chloride. You can dissolve it in water, or you can dissolve it also in liquid ammonia. All right. So let's talk about concentrations. And again, this is something that you would have met before. You would have met molarity before for sure, but there are other ways of expressing concentrations, depending on your need, pretty much. All right. So general definition of concentration is given here. The concentration of a solution is the amount of solute present in a given quantity of a solvent or solution. So we're going to get into the different ways of expressing or measuring concentrations. The first of which is percent by mass. Basically, percent by mass would be the mass of the solute divided by the sum of the mass of the solute and solvent. In other words, this here would be the mass of the solution, right? So we can express it this way as well. The mass of the solute divided by the mass of the solution times 100%, that would be the percent by mass. And then we have what is known as a mole fraction. And you should have met mole fraction in your general chemistry 1 when you were dealing with the gas laws, right? But you can also apply it to pretty much any mixture, right? So the definition of mole fraction, typically represented by the letter X, is equal to the moles of one component, right? The component that you're trying to find the mole fraction of, divided by the sum of the moles of all the components in the mixture, and that would be the mole fraction, all right? And as you can see here, because you have moles divided by moles, that means that there will be no units associated with the mole fraction, all right? Another thing you should recognize about the mole fraction is that it can be no lower than 0, obviously, but it can be no greater than 1, all right? So the mole fraction will range from 0 to 1, all right? Okay, molarity. Now, this one you should be familiar with, right? Molarity by definition is the moles of solute divided by the liters of solution, all right? So that is, by definition, the molarity. Now, there's another way of expressing a concentration known as the molality, right? And please do not confuse molality with molarity. And here's the definition of molality. It is the moles of solute divided by the mass of the solvent in kilograms. All right, so that's the definition of molality. And in terms of the units of molarity can be expressed as M, uppercase M, or moles per liter. And as far as the units of molality is concerned, it can be expressed as lowercase m or moles per kilograms. All right, so these are the separate units for molarity and molality. All right. Okay, and I think the next slide has a question, an example. Yes, okay. So this question says, what is the molality of a 5.86 m ethanol solution whose density is 0.927 grams per mil? So let's put the definition first so that we know what we're working with. So we have the definition of molality and we have the definition of molarity right here. So basically, in order for us to find what the question is asking for, which is the molality, we need two things. We need the moles of the solute and we need the mass of the solvent, all right? How are we gonna find that out? Well, firstly, we're given the molarity of the solution, right? And because the molarity, by definition, is the moles per liter, we can say, okay, let's assume that we have 1 liter of a solution, which means that the number of moles or the amount of moles present would be 5.86 moles. And if you were to convert that to grams, that would be 270 grams, all right? The next step would be to find out, based on the mass of the solution, based on the density of the solution, what would be the mass of 1 liter? And that's the calculation shown here. 1 liter is the same thing as 1,000 mils. So you multiply 1,000 mils by the density, and that gives you the mass of the solution. That's important because what we need to find is the mass of the solvent. So far, we have the mass of the solute and the mass of the solution. So to get the mass of the solvent, what we need to do is find the difference between the mass of the solution and the mass of the solute. And that's what we're doing here, right? So the mass of the solvent will be the mass of the solution minus the mass of the solute. And we just put the numbers in. And it turns out that the mass of the solvent is 657 grams, which is the same thing as 0.657 kilograms, right? So now that we have the mass of the solvent and we have the moles of the solute, then we can find the molality by just plugging the numbers into this equation. And that's what we get, 5.86, which is the moles of the solute, divided by the mass of the solvent in kilograms, which is 0.657, and the answer would be 8.92 M. All right, so that's basically how that is done. All right. Any questions about this example? Any questions? Any questions? Okay. All right, you know what? I think I'm quite sure you're tired of hearing my voice. So what I'm going to do is get you started on assignment number 1. Okay, I just remembered something that I should have mentioned, which is going to be important for you to answering well, actually question 1B, and that is there's another way of expressing concentration. Go back to, okay, now remember what I said about percent by mass, right? That's the mass of the solute divided by the mass of the solution times 100. There's also something I'm going to squeeze in right here, known as parts per million. Parts per million. And basically, it's the same thing as right here, right? So I'm going to write that here. Mass of solute divided by mass of solution. But this time, you're going to multiply that by 1,000,000, 10 to the 6. All right? So we call that parts per million. And this is typically used when you're determining very, very small concentration. It's used a lot by people doing environmental science when they're trying to measure, like impurities in the atmosphere or in water and so on. Usually these numbers are very small. And while I'm at it, let me just give you another one, which is known as parts per billion, which is even a smaller unit. Parts per billion, which is basically the same thing as this, but this time you multiply by 1 billion, which is 10 to the 9. All right, so those are two other ways of expressing the concentration of a solute in a solvent. So for those of you out there in Zoom, let me I'm going to, if I've not done so already, let me go here. Publish assignment number 1. Okay, it's already published. So it's basically on the files, you go to assignments, and you're going to see assignment number 1 published, and you can download it, which is what I'm going to do now. Okay, so the first question is saying a solution is prepared by dissolving 4.87 grams of sodium dichromate in 25 mils of water, and it gives you the density of water. So the first question is, what is the mass percent of water? So it's asking for the mass percent of water in the solution. Let's see if I can turn on my pen here. Okay, so basically there are a couple of ways you can approach this. What you can do, for example, which is probably the most straightforward approach, is that you take, the percent mass of water would be equal to the mass of water divided by the mass of the solution. All right? So how do we get the mass of the water? Well, they gave us the volume of the water and they gave us the density. So how would you find the mass? Anybody can tell me? Write that down here. Mass of H2O. How would you find the mass of water? Yes, sir.
Could it be 1 gram then per milliliter? So it'd just be 25 grams if it's 25 milliliters.
Okay, so how would you set this up? It would be
25 milliliters.
25 mils.
Multiply that by the 1 gram over milliliters.
Exactly.
That's
Right. So that's going to give you 25.0 grams, right? Okay. And then as far as the mass of the solution, that would be equal to what? How would you get the mass? I'm sorry, I'm in your way. Goodness. Okay, how would you get the mass of the solution? Oh, somebody said something online. Let me see. Oh, I don't know. Okay, let me check that out, Mr. Renfro. Oh, no, you don't go to assignments. I'm sorry. You go to files. Let me show you again. You go to files, right? And then you look for the, oh, wait a minute. This is not published. Hold on, let me see here. Okay, that's my fault, Mr. Renfro. Let me check this here. Okay, you should be okay now, right? That's my fault. I neglected to open up the folder here. All right, so let me get back to the question. So, yes, so how do I get the...
Would you add the water and then the sodium?
All right, so you add the mass of the water. Okay, so you add the mass of the water, which we calculated already to be 25.0 grams, to the mass of the sodium dichromate, which is 4.87 grams. So let me take my cheap calculator and work this out. Oh, that would be 29.87. Well, actually 29.9 if they have to round off, because remember, when you're adding numbers, measured numbers, you round off to the lowest number of decimal places, right? So the mass of the solution is 29.9. So we have the mass of the water, we have the mass of the solution, so the percentage of water would be equal to what? What would be the percentage of water?
milliliters divided by 29.9.
But actually 25.0 grams divided by 29.9 grams times 100.
84.0%.
25 divided by 29.9 times 100. And you have to round that off to 3 sig figs. So that would be 83.6%. 83.6%. Okay, any questions about this? Any questions? Any questions? No questions? All right. Is it okay for me to clear all this? So let me go here, clear all drawings. Scroll down. Okay, now this one is asking for the concentration in parts per million. So basically, you're going to divide remember now, parts per million, ppm. is equal to mass of solute divided by mass of solution times 100%. So the mass of the solute is 4.87, right? Okay, 4.87. And the mass of the solution was what? I erased it.
0.9.
So 4.87 grams divided by 29.9 grams times 100%. Let's see what that gives. 4.87 divided by 29.9 times 100. Oh, and by the way, let me just say this. I tell all my students this. If I'm doing some calculation and I'm showing you, and if I go wrong in any way, please feel free to correct me, right? So this is what I got, 16.3%. Yes, sir.
Are we not gonna do multiplying it by 10 to the 6 anymore?
Oh, 10 to the 6. Thank you very much, actually. Thank you. Where's the eraser? Yeah, because it's parts per million. Thank you very much. So it's 10 to the 6, 10 to the 6. So let me correct this here. So it would be 4.87 divided by 29.9 times 10 a million. So the answer here will be 1.63 times 10 to the 5 parts per million. Again, rounded off to 3 sig figs. All right? Okay, any questions about this? Any questions? Any questions? No questions? All right. Let me clear this. Let me scroll down. Okay, so this one is asking for the mole fraction of sodium dichromate, right? So if you remember what we said about mole fraction is moles of solute divided by moles, total moles of solution. And I'm just going to use some symbols here. So typically we use N to represent moles, right? So this would be number of moles of the solute divided by total number of moles of the solution. All right? So we need to find the moles of each of these components in the mixture. Can somebody remind me what the mass of the sodium chromate was what? 4.87, was it?
Yeah.
Okay. And the mass of the water was 25.0 grams, right? So what we have to do is convert each of these masses to moles, right? So how do we convert the mass of water to moles? 25.0 grams. How do we convert that to moles?
You're gonna take the mass of water and you're gonna divide that. So it'd be 25.
I think what you're talking about is the molar mass, right?
Yeah.
You need the molar mass of water. So we get that, of course, by going to the periodic table and adding on the molar masses of 2 hydrogens and 1 oxygen. And you're going to get 18.02 grams, right? So let's work that out. 25 divided by 18.02. This again. 25 divided by 18.02. So according to my calculation, this works out to be equal to 1.39 moles. And then we need to do the same thing for the sodium dichromate, right? So we take the 4.87, and again, just like we did in the case of water, we need to divide by the molar mass of sodium dichromate. So my question to you now is, how do we get the molar mass of sodium dichromate?
The molecular mass.
And how do you get the molar mass?
You add the one sodium and then two chromates.
Well, you need a formula, right? What's the formula for sodium dichromate? Yeah, you might find that table useful that I've provided in Canvas, if you can access it, which gives you the list of ions. All right? Or you can use, or no, you can't use that. That's a periodic table. Well, you're gonna need that for the molar mass, but for the formula, you're gonna need the. What's the formula for the sodium ion? Na what? What's the charge? +1. What's the formula for the dichromate ion?
CR2.
Cr2, I'm sorry?
CR2, O7, -2.
Okay, very good. So how do we get the formula for sodium chromate based on what we have here? Exactly, you're gonna need two of these, so therefore the formula would be Na2, Cr2, O7. So now that we have the formula, we can determine the molar mass. Now, because I'm lazy, I'm going to go to my trusty molar mass calculator, which unfortunately you guys won't have access to do your test. Sucks for you guys. Okay, what's going on here with my, okay. So, if I go here, all I have to do is enter the formula. Na2, Cr2, O7. And let's see. So according to my trusty calculator here, molar mass is 261.97. I'm going to write that down here. 261.97 grams. All right. So going back to the assignment. All right, so let's see what that gives. So I'm going to divide 4.87 by 261.97. And according to my calculation, this works out to be equal to 0.0186 moles. All right. All right, so basically the number of moles of solute would be 0.0186 moles. Am I wrong? So this should be 186 moles. And I have to divide that by the sum of these two, which is 1.39 moles plus 0.018 moles. So what I'm going to do is work out the denominator first, 1.39 plus 0.0186. And that gives 6 moles divided by 1.41. 1.41 moles. All right, so let's see what that gives. 0.0186 divided by 1.41 times 100 So according to my calculation, this works out to be equal to 1.32. The mole units will cancel out, so this would have no units. All right? Any questions about this? Any questions? Excuse me. Oof. Don't know what's going on with my throat. Okay, it's okay for me to clear this. Okay, let's see what's next. Okay, so this has to do with the rule of thumb I mentioned about like dissolves like. It says choose a member in each set that you'd expect to be more soluble in water, right? So basically you're given a pair of compounds and you're to choose which of the two would be more soluble in water, right? Keeping in mind that water is a polar solvent, all right? So let me see what you can come up with in answer to the A part. Ethane, which is CH3, or methyl alcohol. Which of those two would you expect to be more soluble in water? Which one is more polar? Let's put it that way. The methyl alcohol, yeah, which is also called methanol, right? That would be more soluble in water compared to ethane because ethane is non-polar, right? While methyl alcohol is polar. So therefore, you'd expect methyl alcohol to be more soluble. What about potassium chloride or carbon tetrachloride? Which one would you expect to be more soluble in water? And the hint is that potassium chloride is ionic and carbon tetrachloride is non-polar. So which of these two would you expect to be more soluble in water? Potassium chloride, exactly. And then the final one, actually, I don't think that's the final one. Second to final one. Methyl fluoride or hydrogen fluoride. Which of these two would you expect to be soluble in H2O? I'm sorry, what's that? Hydrogen fluoride is indeed correct because hydrogen fluoride is polar. Methyl fluoride is polar, but not as polar as hydrogen fluoride. And then we get to the last one, D, benzene or hydrogen peroxide. Which one of these two would you expect to be more soluble in water? Excuse me. Benzene or hydrogen peroxide, which would you expect to be more soluble in water? Hydrogen peroxide is indeed correct. Okay. I think that's all we can do for now as far as the assignment is concerned. So let me go back to the PowerPoint. All right, so let's talk about solubility of solutes in water. Now, there are different factors that will affect the solubility of a particular solute in water. What we're going to look at is how temperature affects solubility. Firstly, we're going to look at dissolving solids in water. How does temperature affect solubility? And I can just tell you here straight off, and I'm quite sure you know this from your own experiences, like if you're cooking in the kitchen or whatever. Basically, the solubility of a substance in a solvent increases with temperature. All right? And that is shown in this graph here. So let me just explain what this graph is showing you. It's a plot of the solubility of a solute in a solvent versus the temperature, right? And what you'll find is that for most solids, with a couple of exceptions, what you'll find is that the solubility increases. Now, they increase at different rates as the temperature increases, but they all increase excepting some examples or couple of examples, right? So if you look at, for example, potassium nitrate, you see a steep curve right here. So basically, the increase in solubility is kind of dramatic as the temperature increases. But then again, you have some substances like sodium chloride and potassium chloride, which increases, but ever so slightly, and even sodium bromide, very slight increase. But the general trend is that as the temperature increases, the solubility increases. Now, there are a couple of examples where the solubility decreases for solids. One is sodium sulfate, and the other one is cerium 3 sulfate. And the reason for that I won't get into has to do with a lot of thermodynamics involved, all right? So that's basically, generally speaking, the trend that you'll observe when it comes to dissolving a solid in a solvent. Generally, what you'll find is that as the temperature increases, the solubility increases. Now, we can exploit this particular aspect of solubility when it comes to separating a mixture. And let me just say that generally speaking, in chemistry, what you'll find, and this is true at academic levels, true also for high-level research, one common error problem, I should say, that chemists face is separation in order to obtain a pure substance, right? And for those of you who had me in General Chemistry 1 lab, we have done a couple of separation experiments, right? If you recall, right? This is a common problem. Sometimes what happens is that, for example, a chemist might identify, let's say, a compound that exists in some plant tissues, but of course there are other impurities present, and therefore the chemist is faced with the problem of separating or teasing out what he or she wants and leaving behind the impurities, all right? So there are different types of separation techniques depending on the type of mixture. This particular type of technique is known as fractional crystallization. And what it does is that it exploits the difference in temperatures at which the different components in the mixture are soluble in a particular solvent, in this case, water. So let me explain what's happening here. You have a mixture of, well, let me just, before I get to the mixture. So this graph here shows you a plot of solubility versus temperature for two different substances. One is sodium chloride and the other one is potassium nitrate, all right? So as you can see, and I mentioned this before, the solubility of sodium chloride increases gradually. In the case of potassium nitrate, it's a more sharp increase in the solubility as the temperature increases. So let's say you have a mixture of sodium chloride and potassium nitrate where the potassium nitrate is in greater abundance, 90 grams, and it is contaminated with 10 grams of the sodium chloride. So your aim is to basically separate as much as you can the potassium nitrate from the mixture, right? So what you do is, in this particular case, is that you would add this mixture to water at a temperature where both of the substances are soluble, right? So the first step is that you dissolve the sample of water in 100 mils, dissolve the sample in water, and the volume of the water is 100 mils, right? So basically at 60 degrees, that's the temperature where you have a high solubility of both the potassium nitrate and the sodium chloride, right? So as you can see here, at 60 degrees, the solubility of potassium nitrate is 112, so we know that 90 grams will dissolve. And here, for sodium chloride, its solubility is 38 grams per 100 grams, so you know that 10 grams will dissolve in water as well, right? So once you obtain that solution, which is a mixture of those two, you're going to cool the solution to 0 degrees. And the reason why you choose 0 degrees is because at 0 degrees, the solubility of potassium nitrate is now 12.1 grams per 100 grams, which means that some of the 90 grams of the potassium nitrate will come out of solution. At 0 degrees, the solubility of sodium chloride is 34.2 grams. So you know that 10 grams will still remain in the solution in this mixture, right? So basically, all the sodium chloride will stay in the solution, but a certain amount of potassium nitrate will come out of solution. And we can calculate that because we know that 12.1 grams of sodium nitrate will remain in solution. So we subtract that 12.1 grams, where they round it off to 12 here, from the 90, and that gives you the 78 grams of potassium nitrate, which will come out of solution, all right? And therefore, what you can do in practice is that you cold filter it, and you're going to end up with the 78 grams of the potassium nitrate, which should be pure, all right? Now, please note that in a perfect world, you would recover all of it, but you can't do that, right? The best you can recover in this case is 78 grams of the 90 grams that was there in a solution originally. And this is, again, a common issue that people involved in separation face, right? You try your best to separate, as much as you can, or all of it, from the mixture, whatever component that you're trying to isolate, but you just can't succeed. You'll probably succeed in isolating most of it, but not all of it. All right, so that's basically one limitation that we just simply have to live with. All right. Okay, so that's fractional crystallization. Okay, and that's as far as solids solubility in water or solvent is concerned. Now, when it comes to gases, the opposite is true, right? The solubility of gases in liquids is reduced with increasing temperature. And we can see that in the case of the solubility of oxygen in water in this graph here. So the solubility here is on the y-axis, the temperature here is on the x-axis. And as you can see, as the temperature increases, the solubility of oxygen decreases. And this is kind of important, especially when it comes to environmental concerns. I'm quite sure you have all heard of global warming, even if you don't believe in it. And basically, if global warming is something that is actually happening, then of course, the seas and waterways, rivers and so on, will on average experience an increase in temperature, which based on what we have just discussed here, will result in a reduction in the amount of oxygen that would be present in waters, rivers, and so on for aquatic life, right? So basically, this is something that we have to be concerned with when it comes to, aquatic life, fishes, and so on. Okay, so that's basically all we're going to say about that as far as the solubility of gases in water is concerned. Now, the next topic I want to talk about is what is known as Henry's Law. Let me just check something here. Okay, so Henry's Law is talking about the effect that the pressure of a gas will have on the solubility of the gas, right? And basically, in words, Henry's Law says that the solubility of a gas in a liquid is proportional to the pressure of the gas above the solution, right? And we can simply represent it with this equation. C is equal to K times P, where C is the concentration. In fact, I think I have the terms here. C is the concentration of the gas, usually in M, but it can be described in other terms as well, other units. K is, P is the pressure of the gas, and the pressure can be expressed in different units, atmospheres, millimeters per mercury, and so on. And then K is a constant, right? And the constant, of course, is related to the gas, and the constant can be expressed in moles per liter times atmospheres, but this unit here can also be millimeters mercury or whatever pressure units, right? One key thing you need to remember is that the constant is temperature dependent, right? So if the temperature changes, that constant will change. By the way, what time is it? Okay, so that's the Henry's Law right there, all right? So basically, this is a pictorial representation of what Henry's Law is all about. So imagine if you have a gas trapped in this container and you have the liquid here, you have the gas molecules bouncing around, entering into the surface of the liquid, and of course, ends up in a solution or aqueous state, right? And you have this back and forth, right? Some gas molecules will escape into this region here, other gas molecules will enter the liquid, so you have an equilibrium. We're going to talk about equilibrium later on in this course, right? And you're going to see how the equilibrium process maintains a constant amount of gas particles here and here. Now, if you were to add some gas molecules to this, then what will happen is that you're going to have more gas molecules entering into the solution phase, right? So therefore, the concentration of the molecules in the solution will be proportional to the concentration or the pressure of the gas molecules above the solution. So that's basically what Henry's Law is all about. So low pressure means low concentration in the solution. High pressure of gases above the solution will result in high concentration in the solution. Okay, so that leads us now to question number, going back to the assignment. Number 3, all right? So question number 3 says the concentration, let me remind you of the formula here. So right up here. C is equal to K times P, all right? Okay. Okay. Okay, so the question says that the concentration of hydrogen sulfide in hot springs is relatively high. This accounts for the redneck smell around the mud pots in Yellowstone National Park. So it gives you some numbers here. It says that the solubility of H2S at 25 degrees is 0.0923 m at 1.00 atmospheres. If the partial pressure of H2S is 0.12 atmospheres, calculate the molarity of H2S, all right? So remember now, the formula is C is equal to Kp, right? They gave you the concentration at 1 atmosphere, so we can find out what K is. K would be equal to 0.0923 m divided by the pressure, which is 1.00 atmospheres, all right? So that would be equal to 0.0923 m over atmospheres. Now, the question in the second part says that it gives you the pressure as 0.12 atmospheres. You're to calculate the molarity. So again, we're going to use this formula directly this time. So the concentration or the molarity of the H2S in the second part would be equal to K, which is 0.0923 m per atmospheres multiplied by 0.12 atmospheres. So that goes with that. So let's see what that gives, 0.0923 times 0.12. So according to my calculation, this works out to be equal to 0.011, and the units here would be M. And that's how that is done. All right? Any questions about this one? Any questions? Any questions? Any questions? Okay. So I take it it's okay for me to clear this, right? Okay, let me clear that. Let me scroll down. Okay, so let's look at this one. Now, this one is not as straightforward, but it still is using Henry's law. Oops, what did I do? What did I do? Okay. So I'm going to remind you of what Henry's law says. C is equal to K times P. All right, so that's Henry's law, right? So this question says a carbonated beverage is made by saturating water with carbon dioxide at 0 degrees at a pressure of 3.0 atmospheres. And this is a very good example of how Henry's law works, right? All those carbonated beverages that you consume, like Coca-Cola and so on, right? They are manufactured such that the carbon dioxide is under relatively high pressure such that it dissolves in the water, right? And then, so basically, let's say, for example, you have a can of Sprite, right? Basically, right above the surface of the solution, you're going to have carbon dioxide, right? Now, when you crack open that can, right, you're releasing the carbon dioxide from above the surface of the liquid. So you're reducing the pressure of the carbon dioxide above the liquid. What will happen to the concentration of the carbon dioxide in a liquid? It will be reduced. How it's reduced? It escapes, right? So that's why it bubbles, right? And that's the reason why if you leave a can of Sprite or any other soda, exposed to the atmosphere, eventually it's going to go flat, right? The carbon dioxide will escape, especially under high temperature conditions. Because remember what I said previously, right? High temperature will result in a reduction in the concentration of the gas present in the solution, right? So therefore, the solution is going to become flat and you won't enjoy it as much. Okay, so let's look at some numbers that this question is giving. It says that the initial pressure, the temperature was 0 degrees, the initial pressure is 3.0 atmospheres, right? The bottle is then opened at room temperature, which is 25 degrees, and comes to equilibrium with the air in the room containing carbon dioxide, which is the pressure of which is 3.4 times 10 to the minus 4 atmospheres. Henry's law constant for the solubility of carbon dioxide is this at 0 degrees and this at 25 degrees. Okay, so those are some facts given, some numbers given, some data. So the first question is asking, what is the concentration of carbon dioxide in the bottle before it is open? All right, so before it is open, this is the pressure, right? And they gave you the K value at 0 degrees, right? So my question to you is, how would you calculate the concentration using that equation?
Zero point zero seven six nine
Okay,
times per atmosphere
okay.
times 3 atmospheres.
3.0 atmospheres, very good. So the atmospheres unit will cancel out. So that will give us 0.0769 times 3. So according to my calculation, we have to round the answer off to 2 sig figs. So according to my calculation, this becomes 0.23, and the units here would be M. So that would be the answer for the first part. All right? Okay, any questions about that? Any questions? Yes, sir.
Why wouldn't you use the number for 25 degrees Celsius?
Because
Bottles open.
initially, the temperature was 0, so you have to use the value that corresponds to the 0 degrees Celsius. Remember, the K value changes with temperature. So that's the reason why they gave you 2 separate K values at 2 different temperatures. One at 0 degrees, which is before you open up the can of soda, and the other one when everything comes to equilibrium after you open up the can of soda. All right? Okay, any other questions about this? Any other questions? Okay, so I need to clear this and scroll down. Okay, so the question is asking now, what is the concentration of carbon dioxide in a bottle after it has been opened and come to equilibrium with air? So how would you do this part? So let me turn on my pen. So C is equal to what? I'm sorry?
0.0313 moles per.
0.0313 M over atmospheres times
3.4 times 10 to the negative.
3.4 times 10 to the minus 4 atmospheres. This will cancel with that. So let's see what that gives. 0.0313 times 3.4 times 10 to the minus 4. So according to my calculation, this works out to be equal to 1.1 times 10 to the minus 5 atmospheres. All right, so you see that there's a reduction.
Is that atmospheres or moles?
I'm sorry, M. Yeah, thank you. M, all right. And that's it. Okay, any questions about this one? Any questions? Any questions? Yeah. Scroll down to see if there's anything else we can answer. Okay, we can't answer that yet. So let me clear this and go back to PowerPoint. All right, so let's talk about colligative properties. And we're going to talk about the colligative properties of non-electrolyte solutions. So I'm quite sure you know the difference between electrolytes and non-electrolytes, right? Electrolytes are basically ionic compounds, which when added to water, dissociates to form ions, right? And they can conduct electricity and so on, different properties that they exhibit. Non-electrolytic solutions are made up of solutes that do not dissociate, so these are typically covalent compounds, like ethanol or sucrose or glucose, etc., right? So we're going to talk about first the colligative properties of non-electrolyte solutions, and then later on, we'll talk about the same thing for electrolytic solutions. So what do we mean by this term colligative properties? These are properties that depends only on the number of solute particles present in the solution and not on the nature of these solute particles, right? So basically, these properties are not dependent on the nature of the particles. It doesn't matter if the particles are made up of glucose, sucrose, whatever. It is dependent on, or these properties are dependent on the actual number of particles present in the solution. And there are four colligative properties we'll be looking at. One is called the vapor pressure lowering. The other one is called the freezing point depression. Third one is the boiling point elevation. And the fourth and final one is osmotic pressure, all right? So those are the four colligative properties. So we're going to start off by looking at vapor pressure lowering, right? And basically what we're looking at here is the effect of adding a solute to a solvent with respect to the vapor pressure. Now, you may or may not know this, but if you have, draw a little diagram here. If you have, let's say, a beaker with a liquid in it, right? And let's say the beaker is covered or stoppered. So basically you have a closed system. So this is basically the cover, which covers the beaker, right? And this is your liquid right here. And you let it sit for a while. Eventually what's going to happen is that you're going to have up here the vapor of the liquid present, right? So we call the pressure exerted by that vapor the vapor pressure, right, of that liquid. Vapor of liquid will be present, right? So let's say, for example, you have water as a liquid there. You leave it for a while, then eventually above the surface of the water, you're going to have water vapor present, right? And that is true for pretty much all liquids with the possible exception of mercury. And the only reason why I say that is because mercury, its vapor pressure is very, very low, almost zero, all right? So it does have vapor pressure, but it's very low, right? Now, what we'll be talking about here when it comes to vapor pressure lowering is that we're looking at the effect of adding a solute to the liquid to form a solution and how that changes the pressure of the vapor above the solution, right? And what you'll find, as stated here, is that the vapor pressure will be lowered. And we can establish the relationship between the vapor pressure of the solvent in the solution, the pure solvent, to the vapor pressure of the solvent after the solution is made, right? And that's the equation that describes it here. It's called Raoult's law. So let me just give you the different terms. P10 is the vapor pressure of the pure solvent. X1 is the mole fraction of the solvent. And P1 is the, where is it? I thought I had it here. P1 is the vapor pressure of the solvent in solution. All right? So that's a relationship between the vapor pressure of the pure solvent, the vapor pressure of the solvent in the solution, and the mole fraction of the solvent. All right? And what you'll find, of course, is that the vapor pressure of the solvent in the solution will be lower compared to the vapor pressure of the pure solvent. And the reason why that is so, if you look at this mathematically, if you remember I said that the mole fraction cannot be greater than 1, which means that if the mole fraction here is less than 1, that means that this term will ultimately end up being less than this term, right? Now, if the solution contains only one solute, then the mole fraction of one solute, or the solvent, will be equal to 1 minus the mole fraction of the solute. And therefore, we can plug this term into this equation if we want to find the difference in the vapor pressure between the solvent, pure solvent, and the solvent in solution. And when you plug all those numbers in, I won't go through all that now, you're going to end up with that change being equal to the mole fraction of the solute times the mole fraction of the, times the vapor pressure of the pure solvent. All right? Oh, there it is. Okay. The sequence did not come correct here. So that is the vapor pressure of the solvent in the solution. Right. All right. Okay, so that's basically the colligative property of vapor pressure lowering. Whenever you add a solute to a solvent, basically the vapor pressure of the solvent will be reduced as a result of the presence of the solute. And that reduction is expressed in Rayleigh law. All right, let me see here. Okay, now, let's say you have two liquids, right, that are mixed together to form a homogeneous mixture, right? What will happen to the vapor pressure in each case, right? Well, Rayleigh's law will still apply. Now, in this example, we're looking at a mixture of two organic solvents. One is benzene and one is toluene, right? And we're looking at the changes in vapor pressure as the mole fraction of benzene increases. If the mole fraction of benzene increases in this direction on the x-axis, that means that for the mole fraction of toluene, it will increase in this direction, right? So for example, here will be 0, and here's going to be 1.0, right? Okay, so that's basically the plot here. It shows you how the vapor pressure of benzene changes with the mole fraction of benzene, and how the vapor pressure of toluene changes, again, with the mole fraction of toluene, all right? Now, what we're describing here, what I'm about to get into, is what we call an ideal solution, all right? What do we mean by an ideal solution? An ideal solution is basically a solution where the intermolecular forces that exist between the components in the mixture are equal to the intermolecular forces that will be present in the separate components, right? So whatever the intermolecular forces that exist in the separate components before mixing, after mixing, the intermolecular forces are the same, all right? So we call that an ideal solution. An ideal solution basically obeys Rayleigh's law. So let's say that this here represents the Rayleigh's law equation for, let's say, benzene, and this represents the same thing for toluene, right? But we're using A and B in this case, right? So to find the total vapor pressure of the mixture, we simply add these two, PA plus PB, and you're going to end up with this as a result, all right? So that's basically what happens when it comes to mixtures of, well, ideal solutions, right? Where, as I said before, the intermolecular forces between the components in the mixture would be the same as the intermolecular forces separately. And that's what I wrote down here. For an ideal solution, the intermolecular force between A and B would be equal to the intermolecular forces between A and A, and also for B and B, right? So when you have that scenario, you're going to end up with an ideal solution, right? Now, as I said before, this line represents the vapor pressure changes for benzene. That represents the vapor pressure changes for toluene. This line represents the total vapor pressure, which is given by this equation here. So for example, if you want to find out what the vapor pressure of the total mixture is, all you have to do, let's say you're starting from a mole fraction of 0.2 for benzene, which would be 0.8 for toluene. You just draw a line, a perpendicular line, which cuts the curve for benzene, and then you find out what that value is, and then continue that line for toluene, and you find out what that line is, or where that value is. You add this value to this value, and that will give where this line ultimately ends up with when you get to here. So this value here that you're going to get will be the sum of whatever value you get here and whatever value you get here. And that's how you get all the data points to establish that total vapor pressure line for this mixture, all right? So as I said before, we call this an ideal solution. Now, ideal means perfect, and we don't live in a perfect world. So most solutions will not display this particular type of graph. What is more likely to occur for most solutions of two liquids is, we call them deviations from ideal solutions, right? So in this particular case, we're talking about a situation where, okay, This is the line representing the vapor pressure for one component in the mixture. This is the line representing the vapor pressure for the other component in the mixture. So you'd expect that this would be the ideal, this would be what would happen in the case of an ideal solution. What you'll find instead is that the total pressure is this right here, right? So as stated here, the total pressure is greater than what is predicted by Rayleigh law. And the reason why that is so is because the intermolecular forces between the molecules in the solution is weaker or less compared to the intermolecular forces in the separate components that make up the solution. So as a result, you're going to have more gas molecules present or vapor molecules present above the solution, and therefore the vapor pressure will be higher, right? So we call this a positive deviation from Rayleigh's law. On the other hand, other solutions will have this situation where the total pressure is basically on average less than what you'd expect for an ideal solution, right? And in this particular case, this occurs because the intermolecular forces between the molecules in the solution is greater than the intermolecular forces between the molecules in the separate components, all right? So we call this situation a negative deviation from Rayleigh's law, right? So please note that what I showed before was the ideal situation, perfect world, right? But in this particular case, in most cases, you're going to end up with a non-ideal solution, all right? Most of the problems that we'll be working with, we'll be assuming that the solution is ideal, right? But you need to know the fact that non-ideal solutions do exist, all right? Okay, how much time do we have left? Oh, almost done. Okay, I'm going to stop here for today. What you can do in the meantime, let me just check something here, is try on your own question number 5. And question number 6. And let me warn you, question number 6 is going to hit your collective answers. So, we'll try it anyway. All right? Okay, don't forget to turn in the last page completed. I'll collect them right here. And that's pretty, oh, who came in late? Let me make sure I get everybody here. Is Barat here? Burke? Oh, Burke is online, I think. Yeah, I think I remember seeing Burke. Kane? Hollis? Irvin?
Here.
Leonard? Manuel Medina? Unici? And let's see on the other side, Orlando? Renfro? Right? All right, I think that is it. Okay, so yeah, make sure you turn in your last sheet. Listen to us. Right. Yes, sir. Mhm.
Here, 0.6.
I don't remember what I think I had 1.39, if I'm not mistaken. Right, so that's why it's rounded up to 368.
And I got 0 here.
Okay.
You wrote 1.32.
Oh, okay, I'll have to recheck that. We can discuss that first thing next class.
Okay, so the actual answer would be this then.
Yeah, looks like it, yeah. Yes, sir.
So we don't have lab today? Or
We do have a lab class, but you won't be doing an experiment. Basically what I'm going to do is just talk about the syllabus, show you a video on safety, and that's it.
Yeah, I was gonna ask if I could just sign the syllabus beforehand, because I know you want us to turn it in for the lab, or do I have to?
We'll have to wait until we get to the lab class. Yes, sir.
For the homework, I started doing it, I started doing it in, so
Is that okay or?
No, it needs in pen.
Alright.
Yeah. So you can probably trace over it with your ink.
Alright, thank you.
Mhm. Okay, let me get myself together here. Yes, ma'am.
Sir, your class isn't.
But you're on the official list, so how is that? To your people then. Your last name again? I have you here. No, I don't know. You probably need to contact either distant learning or Canvas itself. Yeah, but you're in my class according to this.
Thank you.
Yeah, no problem. Right there, ma'am. Could you bring me that pile of silhouette?
Mr. Really quick.
Yes, sir.
When we are getting the bottom, right there for the moles,
Mhm.
we add these two together, are we gonna do that same concept where you take the least amount of decimals?
Traces, right, exactly,
And
right,
then you would take that number. too.
exactly.
And the whole fraction, the final answer won't have any units?
Yeah, but the moles cancel out.
Oh, okay.
Right, so there are no units associated with mole fraction. Ah. Okay, let me get myself out of here. Yeah, no problem, no problem.